The Big Bang wasn't the beginning of the universe. That statement might sound strange, given that we've become accustomed to counting cosmic history from that moment, treating it as the ultimate starting point. But here's the problem with this common assumption. It's not entirely accurate. Don't misunderstand. The Big Bang theory itself isn't wrong, but it's surrounded by numerous myths and misconceptions. Perhaps the most fundamental misunderstanding concerns what exactly we mean when we use the term Big Bang, which specific moment in cosmic history we're referring to, and which events it actually describes. Many people believe the Big Bang theory describes the creation of the universe itself. However, as we'll explore today, this isn't quite right. The Big Bang theory describes the evolution of the universe, what happened to it from the earliest observable moments of its existence, but not from the very first moment. This means something existed and was happening before what we generally understand as the Big Bang. And we actually have some fascinating ideas about what that something might have been. This isn't about the singularity either, though that concept raises its own questions. You've probably heard that the cosmological singularity refers to a state where the entire universe was compressed into a single point. But here's an interesting question. Isn't the prevailing view today that the universe is most likely infinite? How then could infinity be compressed into a single point? What would an infinitely sized point even mean? We'll attempt to find answers to these questions today, along with exploring what came before the Big Bang, what exactly that phrase means, what problems exist with the standard Big Bang model, and how cosmic inflation helps solve them. Understanding how the incredible diversity of countless planets, stars, and galaxies could have emerged from apparently nothing is almost as difficult as grasping the concept of infinity itself. The classic Big Bang theory, as it existed before the 1980s, couldn't explain these problems. That's where cosmic inflation comes in, a proposed early period in the universe's history when, in an incredibly brief instant, it expanded in size by an enormous factor. Let's quickly review the key milestones. In 1915, Albert Einstein published his general theory of relativity, which allowed discussion of space-time structure and universal evolution in terms of concrete physical laws. In 1917, Einstein himself applied his theory to describe the entire universe and was surprised to find that his results contradicted the prevailing notion of a static universe. His solutions showed the universe should be expanding or contracting. Uncomfortable with this contradiction, he introduced the cosmological constant into his equations, which allowed the universe to remain static. Later, of course, he abandoned this constant, though it eventually found its way back into cosmology. In 1922, Alexander Friedmann solved Einstein's equations and obtained results showing the universe could be homogeneous, isotropic, and crucially, not static. Unlike Einstein, he wasn't frightened by these results. His solutions described three possible universes with three different geometries and corresponding evolutionary paths: a closed universe, an open universe, and a flat universe. He was among the first to propose that the universe might have had a beginning. In 1927, Georges Lemaitre described an expanding universe and later introduced the concept of a primordial atom from which the universe was born, what we now call the cosmological singularity. This eventually became the Big Bang theory, ironically named in 1949 by Fred Hoyle, an ardent opponent of the expanding universe model. This came despite Edwin Hubble's 1929 observational discovery of universal expansion through observations of galaxies receding from us at velocities that increased with distance. Beyond observed universal expansion, two other major pillars support Big Bang theory: primordial nucleosynthesis, and the cosmic microwave background radiation. Earlier theories proposed all chemical elements formed either in stellar cores or supernova explosions, but predictions didn't match observations well. George Gamow and colleagues developed a theory that light elements like helium and certain isotopes could have formed in the early universe as it cooled during the first minutes after what we might call the beginning. Their theory predicted 25% of matter in the universe should be helium, an explanation consistent with a hot, dense early universe described by hot Big Bang theory, and importantly, consistent with modern observations. We indeed observe such matter distribution as primordial nucleosynthesis predicts. And of course, the cosmic microwave background radiation. If the universe was dense and hot, residual radiation from that period should remain uniformly distributed throughout the universe, radiation that could freely propagate once the universe expanded and cooled sufficiently. This radiation was predicted in 1948 by Robert Herman, Ralph Alpher, and again George Gamow. In 1965, it was discovered by Arno Penzias and Robert Wilson. The radiation's temperature and properties proved remarkably close to predictions. All this data and subsequent observations eventually made Big Bang theory the primary explanation for universal evolution. Common misconceptions probably arise from the name Big Bang itself, and from animations that make it seem like there was some point serving as an explosion center, with everything flying outward from it. People naturally ask where the universe's explosion center is now. Such animations aren't perfect scientific representations, much like solar system diagrams that sacrifice accurate scale to fit all planets in one image. These pictures and animations give us a general understanding of structure, but you certainly couldn't use them to plan spacecraft trajectories. Similarly here, these animations show us the fact of universal expansion, but they're not precise, and in some ways actually incorrect. Another point worth mentioning is the question of singularity and universal infinity. Singularity is problematic, just as with black holes. Whenever singularities appear in solutions, regions of infinite density and similar extremes, it likely indicates we don't fully understand something. If we mentally rewind time, everything in the universe becomes closer together until we could reach a singularity where everything compressed to a point. But here, familiar physical laws stop working and cannot describe what should happen with this singularity. Yet in brief, popular explanations of Big Bang theory, singularity is almost always mentioned. So how do you compress an infinite universe into a point? Actually, this question can be reformulated more conservatively. We don't even need to reach the singularity. We could stop not at a point, but at a very small size. The question remains valid. How can you make infinity small? In other words, how can something infinite change size? The key is that when we discuss an expanding universe, it's more correct to speak not about how its size changes, but about how distance between, say, two galaxies changes. This change in distance fits into a parameter called the scale factor, an extremely important parameter in Friedmann's equations. This parameter is dimensionless, meaning it has no units of measurement like meters. In the present time, when the universe's age is approximately 13.8 billion years, and the observable universe's radius is approximately 46.5 billion light years, the scale factor is assigned a value of 1. The further into the past, the smaller this parameter. For instance, at a scale factor of 0.5, the age is 5.8 billion years, and the horizon is 18 billion light years. At 0.1, we're at 4% of the universe's age, and so on. What does this tell us? The entire universe could be infinite. Simply, The further we look into the past, the smaller the distance between 2 points, the more densely concentrated matter was. Speaking about size becoming larger or smaller really applies only to what we call the observable universe, the piece of universe limited by the particle horizon beyond which we fundamentally cannot see. But beyond the horizon, the universe probably continues, quite possibly the same universe with the same properties, physical laws, galaxies, stars, and so forth. So if the universe were finite with some boundary, we could somehow imagine everything in the universe compressed to a point. But in the case of an infinite universe, speaking of a point becomes more difficult. More likely, we can assume the universe was already infinite, just with everything closer together and denser. But there was no point and no explosion center. Not that the infinity story is much easier to grasp mentally, but at least speaking about the evolution of the scale factor is more correct than speaking about the size of the entire universe. And if we must discuss size, we should specify the observable universe. But if before the expansion we describe with Big Bang theory, the universe was already infinite, then what was there at all? This is where inflation can help. Despite Big Bang theory's success in describing universal evolution within certain timeframes, it has serious problems. There are usually 3 main problems discussed: the horizon problem, the flatness problem, and the monopole problem. Inflation can serve as a solution to all 3. What's the horizon problem? As mentioned repeatedly, we find ourselves at the center of the observable universe, inside a kind of bubble with finite radius, bounded by the particle horizon. This is all the universe we can currently see, and 2 factors limit this: the finite speed of light and the finite age of the universe, since the moment light could freely propagate. Light has had only a certain amount of time to reach us, and the most distant radiation we can register is the cosmic microwave background. We can imagine ourselves at the center of a sphere, on whose inner surface we observe this radiation. This surface is called the surface of last scattering. One interesting property here is that we can observe regions of the universe where hypothetical observers cannot observe each other. Imagine us at the center of our observable universe, with our horizon or observable universe boundary around us. The universe is likely larger, probably continuing beyond our horizon. But if an observer exists elsewhere, they would have their own horizon. And if an observer sits on our horizon, we're on their horizon, or at the edge of what they can observe. What if we place 2 observers at opposite ends of our observable universe? We can see them both, but they cannot see each other. Each has their own horizon, and since the universe began, insufficient time has passed for light from one observer to reach the other. This means these 2 regions of the universe had no way to exchange information or influence each other. Modern measurements of cosmic microwave background radiation show it's extremely uniform throughout the universe. While maps of this radiation look varied and colorful, the temperature fluctuations across the entire sky are actually tiny. Modern measurements show the temperature everywhere equals approximately 2.73 Kelvin. The variations across the sky represent changes of about 1 part in 10,000 or even 100,000. In reality, the cosmic microwave background is extraordinarily uniform across the universe. So what's the problem? Identical temperature is a property of thermal equilibrium. This means at the moment cosmic microwave background radiation appeared, in the very early universe, it was already in thermal equilibrium. But usually, for some volume of matter to reach thermal equilibrium, different parts of that matter must interact with each other. If we take 2 containers, one with hot gas and one with cold gas, and open a barrier between them, The substance reaches thermal equilibrium when the gas mixes and temperature becomes uniform throughout the volume. But we've already established that we observe parts of the universe that couldn't have interacted with each other. How then did they reach thermal equilibrium? Why do we see such uniform cosmic microwave background radiation? How do distant parts of the universe know about each other's properties without any possibility of interaction? This is the horizon problem. The mechanism by which the universe could have achieved equilibrium in the available time isn't understood. We could, of course, attribute everything to initial conditions, saying it simply was that way from the start and accepting it as given. That could be an answer, but not a very satisfying one. It's like the fine-tuning problem of the universe in general. Simply saying that's how everything was and accepting it gives us no knowledge about how the universe works and evolves. Next, we have the flatness problem. Speaking of fine-tuning reminds me that space-time geometry and critical density are among the sharpest questions in universal fine-tuning. In brief, fine-tuning refers to a situation where our universe seems specifically configured to allow structures like stars and galaxies and life itself to exist. It appears that a considerable list of universal parameters have exactly the values that permit both structure and life to exist, which seems too unlikely to be mere coincidence. And why do we speak specifically about universal flatness in the Big Bang context? The problem is already quite acute, but the Big Bang makes it even more severe. Recall that depending on how much total matter exists in the universe, its fate and shape could differ. There's a parameter called critical density. Critical density equals exactly 1. If there's too much matter, density exceeds 1, the universe could have closed geometry, gravity wins, and after starting to expand, it might collapse back. If matter is insufficient, density is less than 1, it has open geometry, and at certain density values expands so rapidly that no structures form. But there's also a middle option, precisely when density equals 1. There's exactly enough matter in the universe so it doesn't collapse back, but also doesn't expand too rapidly. This is roughly speaking. Modern measurements show density in the universe, if not equal to critical density, is very, very close to it, and universal geometry is flat. Usually people say the universe balances on a knife's edge and express amazement at the extremely low probability that density would randomly take precisely this necessary value, exactly in the middle of an enormous range of possible variants. But why is this specifically a Big Bang theory problem? Supposedly, flat geometry and density equal to critical density represent an unstable, special situation. And if it's close to or equal to critical density now, it must have been so from an earlier cosmic epoch. Even slight fluctuations could have led to very significant universal changes, and in the early stages of its evolution, this problem becomes even more acute. For us to observe today the universe we observe, in the first moments of the universe, the density value shouldn't have deviated from critical density by more than a fraction of 10 to the negative 64th power. Deviate just slightly by such an unimaginably tiny fraction, and the universe would be different. No wonder people think about fine-tuning. Again, we could simply accept this as given and conclude we were just extraordinarily lucky, which some people do. However, others believe such a coincidence demands an explanation. Finally, the monopole problem. There are 4 forces, or more precisely, fundamental interactions governing the universe: gravity, electromagnetism, strong and weak interactions. At extremely high energies in the very early universe, these forces were unified. As the universe expanded and cooled, symmetry breaking occurred, and these forces separated. According to grand unified theories, this symmetry breaking should have produced magnetic monopoles, hypothetical particles with only one magnetic pole, either north or south. The problem is, we should observe these monopoles in enormous quantities if they were produced during this phase transition, but we've never observed a single one. Classic Big Bang theory existing before the 80s couldn't explain these problems. That's why it needed an addition in the form of inflation. Throughout almost all of its existence, the universe has been expanding in a gradual manner. For the first several billion years, expansion velocity gradually decreased. Then dark energy began dominating, and expansion started accelerating. But there may have been a period in the very early universe when the universe didn't just expand. It expanded like mad. It expanded exponentially, doubling in size. Or more precisely, the distance between two arbitrary points doubled every unimaginably tiny fraction of a second. And when 10 to the negative 33rd power seconds had passed, 1 billion trillionth of a second, an extremely small fraction of a second. During this time, the universe expanded by a factor of 10 to the 30th power, 1,000 billion times. After inflation, expansion slowed down, entering the normal expansion regime already described by hot Big Bang theory. The idea of inflation was proposed in 1981 by Alan Guth. In his original description, before expansion began, the universe was in a false vacuum state. This state is metastable, meaning it can remain in this state for a long time, but there's a chance of spontaneous transition to true vacuum. We can use the analogy of supercooled water. Water can remain liquid below its freezing temperature if it's pure and undisturbed. But if you disturb it, usually a small crystallization center forms, and the entire volume of supercooled water rapidly transforms into ice. Similarly here, the universe before the Big Bang was in a false vacuum state. As a result of, for example, random quantum tunneling, a microscopic region of true vacuum appeared, which rapidly expanded and eventually became our universe. But this idea had problems. For instance, there wasn't really a mechanism for exiting the inflationary state. Or what if such bubbles could arise in large numbers in such a universe, colliding with each other, which would lead to observable universe inhomogeneity that we don't see? This version is now known as old inflation. Its shortcomings became clear fairly quickly, and already in 1982, Andre Linde, Paul Steinhardt, and Andreas Albrecht proposed a version of new inflation. The key difference in new inflation is that the phase transition to true vacuum here is second order rather than first order, and the transition, or rolling down to true vacuum, is now slow. This variant required less fine-tuning and allowed inflation to end naturally. You might ask a fair question: where exactly did all this happen? Here it's proposed that before our universe arose, a hypothetical inflaton field existed. Today, the universe is fairly successfully described by quantum field theory, according to which fields spread throughout the universe, and at every point in space, these fields have certain values. All particles, electrons, photons, quarks, aren't little balls, but rather excitations in these fields. The inflaton field is a field responsible for inflation. This field had a certain potential energy, and as the field rolled down from higher to lower energy states, this drove the exponential expansion. It turns out inflation elegantly solves the three major Big Bang problems. Let's start with the horizon problem. Before inflation, when the universe was incredibly tiny, regions that are now on opposite sides of our observable universe were actually close enough to be in causal contact, close enough to reach thermal equilibrium. Then inflation occurred, expanding the universe by an enormous factor in a tiny fraction of a second. Regions that were previously in contact were suddenly stretched so far apart that light hasn't had enough time since then to travel between them. They're now beyond each other's horizons, but they retain the properties they had when they were in contact, which is why we see such uniform cosmic microwave background radiation today. The flatness problem is also resolved. Inflation stretched the universe so enormously that any initial curvature was flattened out, much like how the surface of a balloon appears flatter the more you inflate it. After sufficient inflation, the universe would appear extremely flat regardless of what its initial geometry might have been. Any deviation from critical density would have been diluted to negligible levels. This explains why we observe the universe to be so close to flat today, without requiring incredibly precise initial conditions. As for the monopole problem, if magnetic monopoles were produced before inflation, they would have been diluted to such an extent by the exponential expansion that the density of monopoles in our observable universe would be essentially zero. Inflation spread them so thin that we wouldn't expect to find any in our observable patch of the universe. This neatly explains why we don't observe them despite theoretical predictions of their creation. After inflation ended, a crucial process called reheating occurred. During inflation, most of the energy was in the inflaton field itself. When inflation ended, this field began oscillating around the minimum of its potential. These oscillations led to particle production, converting the inflaton field's energy into ordinary matter and radiation. This process is complex and involves parametric resonance, sometimes called preheating, where particles are produced very efficiently through non-perturbative effects. The universe transitioned from a cold, empty state dominated by the inflaton field to a hot, dense state filled with particles, the state described by standard Big Bang theory. This is when the hot Big Bang phase truly began. One fascinating aspect of inflation is that quantum fluctuations in the inflaton field during the inflationary period got stretched to enormous scales. These tiny quantum fluctuations became the seeds for all the structure we see in the universe today. Regions that were slightly denser than average eventually collapsed under gravity to form galaxies, stars, and planets. The pattern of these fluctuations is imprinted in the cosmic microwave background radiation as those tiny temperature variations we observe. Modern precision measurements of these fluctuations have provided strong support for inflationary theory, as the predicted pattern matches observations remarkably well. However, inflation raises its own intriguing questions and possibilities. Some models of inflation, particularly those involving eternal inflation, suggest that inflation never truly ends everywhere. While inflation ended in our region of space, creating our observable universe, it might continue forever in other regions, constantly creating new bubble universes. According to eternal inflation, once inflation starts in some region, quantum fluctuations ensure that in some parts of space, the inflaton field value remains high enough that inflation continues there, even as other regions exit inflation. This process continues indefinitely, producing a potentially infinite number of separate bubble universes, each of which could have different properties. This leads to the concept of the multiverse, where our universe is just one bubble among countless others in an eternally inflating space. Each bubble universe would have undergone its own Big Bang when inflation ended in that region. The different bubbles might never interact with each other, because they're separated by regions of space that are still inflating and expanding faster than light can cross them. Some physicists find this multiverse scenario compelling, because it could potentially explain fine-tuning. If there are countless universes with different properties, it's not surprising that at least one would have the right conditions for life. We necessarily find ourselves in one of the universes capable of supporting observers. However, the multiverse interpretation remains controversial. Some scientists argue it's not truly scientific because we can never observe or test the existence of other universes beyond our cosmic horizon. Others counter that eternal inflation is a natural prediction of our best inflationary models, and we shouldn't dismiss predictions simply because they're difficult to test directly. The debate continues, representing one of the frontiers of modern cosmology. It's worth emphasizing what we mean when we say the Big Bang wasn't the beginning. In the classical Big Bang picture, we extrapolate backward in time to a singularity, a point of infinite density and temperature where physical laws break down. But we now understand this extrapolation has limits. As we approach the Planck time, approximately 10 to the negative 43 seconds after the nominal Big Bang, quantum gravitational effects become important, and we don't have a complete theory to describe what happens. The singularity is likely not a real physical object, but rather a signal that general relativity breaks down at extreme conditions. Inflation provides a different picture. According to inflationary theory, the hot Big Bang phase, the expanding, cooling universe filled with particles and radiation, was not the true beginning. It was preceded by the inflationary epoch, a period of exponential expansion driven by the inflaton field. And inflation itself presumably had a beginning, though we're less certain about what preceded it. Some models propose the universe could have existed in some form before inflation began, perhaps in a state of false vacuum that had existed for an indefinite time before tunneling to create our inflationary epoch. Current observational evidence strongly supports inflation. Measurements of cosmic microwave background radiation by satellites such as COBE, WMAP, and Planck have revealed patterns consistent with inflationary predictions. The near-perfect flatness of the universe, the Gaussian distribution of temperature fluctuations, and the scale-invariant spectrum of density perturbations all match what inflation predicts. The famous data from the Planck satellite showing the cosmic microwave background's temperature variations represents our best view of the universe when it was only 380,000 years old. Those variations encode information about what happened during inflation. Recent research has focused on refining inflationary models and searching for more definitive evidence. One key prediction of many inflationary models is the production of primordial gravitational waves. These would leave a distinctive polarization pattern in the cosmic microwave background called B-mode polarization. Detecting this signal would provide smoking gun evidence for inflation and would tell us about the energy scale at which inflation occurred. Several experiments are currently searching for this signal, though initial claims of detection have not been confirmed. The search continues with increasingly sensitive instruments. Scientists also debate which specific model of inflation best describes what actually happened. There are dozens of proposed inflationary models, differing in the details of the inflaton field's potential energy curve and how it couples to other fields. Some models predict slightly different observable signatures, such as variations in how the density fluctuations depend on scale or different amounts of gravitational waves. As observational precision improves, we may be able to distinguish between these models and narrow down which version of inflation, if any, correctly describes our universe's early history. An important conceptual point about inflation concerns the nature of the expansion itself. During inflation, space itself expanded faster than the speed of light. This might sound like it violates special relativity, which states nothing can move faster than light. But there's no violation because special relativity, restricts how fast objects can move through space, not how fast space itself can expand. General relativity, which describes gravity and the dynamics of space-time, places no limit on how fast space can expand. During inflation, galaxies weren't moving through space faster than light. Rather, the space between them was expanding at an enormous rate. This distinction is important for understanding how inflation solved the horizon problem. The regions we observe on opposite sides of the sky weren't always beyond each other's horizons. In the incredibly tiny, incredibly early universe before inflation, they were close enough to interact and reach equilibrium. Inflation then stretched space so rapidly that these regions were carried beyond each other's horizons. They've been causally disconnected ever since, yet they retain the uniform properties established when they were in contact. This is why we see the same temperature cosmic microwave background radiation in all directions. The implications of inflation extend beyond just solving cosmological problems. If inflation is correct, it tells us something profound about the nature of reality. It suggests that the observable universe, everything we can see even in principle, is just a tiny fraction of what exists. The part of the universe we can observe is limited by how far light has traveled since the Big Bang, giving us an observable universe radius of about 46.5 billion light-years. But if inflation occurred, the actual universe is vastly larger, perhaps infinite. Most of the universe lies forever beyond our ability to observe. This has philosophical implications. It means there could be vast regions of space we'll never see, places where the same physical laws operate and where matter is arranged in galaxies and stars, much like our own region. There might be countless other observers in these distant regions, living out their lives completely unaware of our existence, just as we're unaware of theirs. If the universe is infinite, as inflation suggests it might be, then every possible arrangement of matter that's consistent with physical laws occurs somewhere, repeated infinitely many times across infinite space. From a scientific standpoint, inflation represents a remarkable success story. It was proposed to solve specific theoretical problems with the Big Bang model, and it made testable predictions about the observable universe. Those predictions have been confirmed by precise measurements. The temperature fluctuations in the cosmic microwave background, the large-scale structure of galaxies, and the overall geometry of space all match what inflation predicts. Few theories in the history of science can claim such success in predicting observations that weren't available when the theory was proposed. Yet questions remain. We still don't know what the inflaton field actually is, or how it relates to other fields in particle physics. We don't know with certainty which inflationary model correctly describes what happened. We don't know whether inflation was eternal, producing a multiverse, or finite, producing only our single universe. We don't know what, if anything, preceded inflation, or what caused it to begin. These questions push us toward frontiers where general relativity and quantum mechanics intersect, realms where we don't yet have a complete theoretical framework. Some physicists have proposed that a complete theory of quantum gravity, perhaps string theory or loop quantum gravity, will ultimately explain what happened at the very beginning, including what preceded inflation, or whether the question even makes sense. Others argue that there may be limits to what we can know about the very earliest moments of cosmic history, that some questions about ultimate origins may lie beyond the reach of science. These debates continue as researchers work to push our understanding ever further back in time toward that first instant. Meanwhile, observational cosmology continues advancing. New telescopes and detectors are being built to study the cosmic microwave background with even greater precision, to map the large-scale structure of the universe more completely. and to search for primordial gravitational waves. Each new observation provides another piece of the puzzle, helping us understand not just what the universe looks like, but how it came to be this way. The next few decades promise exciting discoveries as these new instruments come online. In conclusion, when we talk about the Big Bang today, we need to be precise about what we mean. The classical Big Bang picture of a universe emerging from a singularity has been superseded by a more sophisticated understanding involving inflation. The hot Big Bang phase, where the universe was extremely hot and dense and began expanding and cooling, creating particles and eventually atoms, stars, and galaxies. This was not the beginning. It was preceded by inflation, a period of exponential expansion that set the stage for everything that followed. Inflation explains why the universe is so uniform, why it's flat, and why we don't observe magnetic monopoles. It makes predictions that match observations and provides a framework for understanding cosmic history. Whether inflation itself had a beginning, what if anything preceded it, and whether it continues eternally creating a multiverse, these remain open questions at the cutting edge of cosmology. What we can say is that the universe's story is far richer and stranger than a simple explosion from a point. It's a story of quantum fields and exponential expansion, of horizons and causality, of structure emerging from quantum fluctuations, a story that science continues to unravel through theory and observation, pushing ever closer to understanding our cosmic origins.